the reason, that I'm up here is, this beautiful effect that we had last night. So there was apparently a lot of rain here. When I came here, I looked out of the window and I saw that, and I saw, wow, we are right at the bucket place, where the rainbow touches the campus. Coming from Europe this morning, I was, up very early and could prepare my talk. So I'm a numerical physicist, and I will talk about numerical techniques that we want to apply to quantum many-body systems and look for interesting things. And Yuna recruited me to talk about machine learning. So we want to take a computer and make it learn a lot of stuff, and at the end of the day, it will realize what Schrödinger's cat is. That's the very ambitious program for today. I'm set up to give 2 talks today, 2 lectures. This is the first one. This first lecture, I will talk about machine learning and give you an introduction. This is mostly a talk, as you would hear it, in a computer science department. So there's not much physics in the morning. In this first lecture, I will here and there, start to make connections where we can apply, certain techniques to more physical problems. But mostly I will introduce nomenclature and, get rid of, some illusions about machine learning and introduce some notions. I think this is important because, machine learning is in everyone's mind right now, but we need to understand, these concepts first before we go. So it's an introduction driven to physicists, so to you, so you're very much encouraged to interrupt me at any time and then ask questions. Understanding these concepts in the morning will be an ingredient to follow what we want to apply these to in the afternoon. Okay, so let's get started, and let's start a little bit dry, with setting the perspective. So what's machine learning? So if you walk over to the CS department here in Cornell, it's actually a very strong one, and ask what is machine learning? They will tell you, well, machine learning, it's like everything that we do here is about algorithms. It's about algorithms that we use for data analytics, and then they will say words like dimensional reduction and feature extraction that they want to achieve by using these algorithms on data, big data, and so it's about manipulating data and extracting interesting stuff from this. And dimensional reduction means it's a lot of data and it's only a few features that you get out at the end of the day. You're accustomed to machine learning algorithms already today because they come built in a lot of software programs and apps that surround you. Independent whether you're a Microsoft person or an Apple person, you will appreciate things like a spam filter in your email. So somehow your computer reads your email and decides, whether, from, the lot of data that is in there, that's a relevant email for you or not, and sorts it into your spam folder, in certain cases, and in others, it will highlight it as, a very relevant email that you should quickly be reading. Things like face recognition, that's actually a lot of fun if you have a Microsoft Surface, this laptop that opens up and you look at it and it will unlock. So that's pretty cool, and it's pretty amazing that that is a technology that is available, and reliably available. And we will see why that is. We will see why that is available today, and hasn't been available 5 years ago. You know this from your photo apps as well. Face recognition 10 years ago would slow down your laptop to incredibly, slow status. Today, it will immediately recognize a face, while you're taking a picture, and use the autofocus to do this. Voice recognition is underlying a lot of technology as well. You can talk to your computer, ask it a question. Why is every plane delayed to Ithaca tonight? Because there's a storm. Skype, is coming out with simultaneous translation. You can talk to your collaborator overseas and speak your home language, and he will hear whatever he wants to hear. It's pretty amazing that these things actually work. About apps, that start to become hardware objects and come in your life. So apparently we all need, besides our many digital assistants that we have, one more one, like this Echo from Amazon, that allows you to order stuff or play music, or ask another question while you're sitting in your living room, or have your car drive you around. You're also getting accustomed to the fact that using these types of techniques, all kinds of things can go wrong. You might end up ordering toasters, many toasters that you never wanted. Your car might go places that you haven't seen. Yeah. So machine learning apparently is also something where machines learn, but they can also fail. Let's understand all these things. Probably the most dramatic step in all this for people to realize that something is brewing up in the computer science departments is when computers start to play. Yeah, and for the older ones, we are accustomed to this concept. When in '96, the first time a computer from IBM, IBM's Deep Blue, was playing chess against Kasparov, and it was beating the shit out of the guy. Yeah, so the computer learned to play chess. Well, chess turned out to be relatively simple type of game that you can learn. It's something that you can try to predict which are the next 2, 3, 4, 5 steps that your competitor might envision to do, and you try to calculate which one is the best one you can do. The more ancient game of Go is much more complex, in terms of predicting moves. So this type of predictability is nowhere there. So it was even more impressive that 20 years after chess, Go was played by a machine, Google's AlphaGo, and would beat one of the world-leading Go players. So my Asian colleagues, they tell me that is really what made them believe that computers can create their own knowledge, because Go is played by tradition. Yeah, so it's a lot of knowledge, how you play, that is transferred from generation to generation of Go players. And there's a certain context in which you play. Okay, so I don't know about these things, and that's what these guys master. And the machine won by going out of tradition. Yeah, it would start doing things, open the fifth row, yeah, which you're not supposed to do. Yeah, but it did it and it won. So somehow it found out a trick, yeah, that hasn't been there for years and years. And this is when people say, oh wow, this thing is intelligent. Yeah, so this is when you talk about artificial intelligence in the context of these things. So all these things, that I've shown, your email filter, your digital assistant, your car, or the Go playing computer, they're using very similar, technology, in order to do that, the machine learning stuff that they do. So this is what we want to learn today. Yeah, so we want to understand how do machines learn? Yeah, what is it that they can learn? Yeah, how do we control, what they learn? And how can we do this to our own benefit? Yeah, so our own benefit, not as a customer, but probably as a physicist. Yeah, and then there is this miracle thing, that somehow neural networks are used, and we have some diffuse, as physicists, we only have some diffuse understanding of biological neural networks, and then there's these artificial neural networks that are apparently used in the context of machine learning. Okay, so let's start here. Yeah, so let's understand what artificial neural networks are, how they're built up, and how they are working, yeah, in order to understand something. So let's go there. As I see some of you are taking photographs while I speak, that is certainly not necessary. I'm sure there will be a web page of the school where these slides will be collected.
All the lectures are being recorded back there. So you don't necessarily have to take notes or take pictures. You'll be able to see everything.
Exactly, yeah.
And the slides will be also available.
Yeah, so the slides will be available. They will also be available on my webpage. And they will be much better than photographs because they will have links like this one. So if you want to learn about artificial neural networks and deep learning, there's a very nice book, a book by Michael Nielsen, whom some of you might know from his book about quantum information theory. He has written another book, which is only available as an online book at neuralnetworksanddeeplearning.com. Okay, so it's much nicer to click on this and write this down. Yeah, gives a very nice introduction, written by a physicist for a physicist, into this field. Yeah, so a great place to start if you want to enter this field. Good. So what's an artificial neural network? Well, something like this. Yeah. So it's a network of constituents which are artificial neurons, these dots here, they're connected, and as such, they somehow try to mimic a biological neural network. First thing to realize is, we will be dealing with, something like this. So networks that are, made of a few tens or a few hundreds of constituents, while, the stuff in your brain has a couple of, billion of these constituents. So we are on a very different scale. The physicists, we immediately understand, that scale is relevant. So probably what we will do is a, super simplification of, anything that might be there in biology. Yeah. Okay. So, so we will be dealing with these kind of network structures. Yeah, we will, look deeper into, how they're built, what they do in a minute. What they will allow us to do is they will allow us to represent knowledge. That sounds very abstract. In an implicit way. Yeah, so somehow, stuff goes in on the one side of the network, other stuff comes out on the other side, and knowledge is between there. Yeah, and works on the input and generates some output. And it will not be easy for us to, see how this knowledge is actually created and how it is actually stored, as opposed to very explicit ways. So you could come up with, other things. There's, artificial intelligence is built on explicit knowledge representations. Like, if you try to mimic what a doctor does, when he sees you. So he scans you and says, oh, this is a male in his mid-years, yeah, and he has, I don't know, little red spots on his face, let me look up. That means I should probably check, whether he has, red spots all over his body, and, he can go through, steps like these, and you can, take a computer and, follow these steps, that the doctor takes, when he does so. And that would be explicit knowledge representation. You say, well, these, are, 200,000 different steps you can take when you see a patient, why don't you do those? Of course, that might be an oversimplification of what a doctor does, but this is not what we will be doing here. So here, there's no such explicit recipe, that is somehow encoded here. It's implicit. Okay, so there's no direct way for us to say precisely where knowledge is stored and what it actually is. And how do we get it in there? Well, there will be different types of learning techniques, so different ways of making the neural network, this artificial neural network, acquire this knowledge, and they're called supervised and unsupervised learning. So these things, we want to understand. Okay, so let's start with the basic ingredient. Let's start with one of these artificial neurons and understand now in a more mathematical way what it actually means to be such a neuron, and then we will understand the entire network in terms of mathematical language. Yeah, so that's for us physicists, that's very important. So here's the artificial neuron. So one neuron, a couple of inputs, and let's start with this simple case. Probably it's a binary input. So there's a couple of legs coming in here, and every input leg, x1, x2, x3, has some value. It goes into the network. It goes into the artificial neuron, and it's weighted. So every input has some weight associated with it. W1, W2, W3. Goes in here, and then when it's in there, it's compared to a bias. That's a speed, it's a number. And then it generates an output. And what it will do is, it will calculate, the scalar product of all the inputs, with all the weights, and compare that to that threshold value, that bias value. And if you're above that threshold value, then the neuron will fire. It will generate a positive, output 1, and in the other case, it will not. So the neuron will just, encode, the step function. So, if all these inputs are below the threshold B, there's no output 0, and if it's above, it fires. That means it jumps to 1. Creates an output, and that output can go into, the next neuron or be the final output of the network.
Question: are these weights positive, definitely?
So no. So let's do this by example. So let's try to take a single neuron and see, what its capacity is. So, you in this morning, like, my cohort of speakers, ask yourself this very principal question: should I skip the first talk? So you have a couple of, inputs, that you consider there. So is there free coffee? Is there deep learning? And really no topology in the first talk? So you will put weights on these things. And then, have some bias, and then come to some decision. Okay? So
Free coffee is plus 10, by the way.
Yeah, that's really your preference is here in the weights, yeah. And now you see, no topology, -4 for me, +1 for you, I don't know, yeah. And yeah, also the spies, I don't know, yeah. So this is where you can play with these things, okay. But you see, already a single neuron can make this type of decision, yeah. So that's good. So let's make this more systematic. Let's look at what looks like a very simple situation. I take a binary input, 2 input variables which are now binary, given weights and biases. And now let me see what I actually can generate with that. Yeah? So I can make this binary table of inputs and outputs. And I see that, aha, this artificial neuron itself realized what we call a NAND gate in binary logics. Yeah? So it generates exactly this desired output for these 4 possible binary inputs. So that's actually a very important information because we know something about the NAND gate. The NAND gate, in terms of circuit building, is a very powerful one. It's the only one that you actually will need. If you want to build any logical circuit, you can build it solely from NAND gates. So it's a gate that we call computational universal. So whatever cool code you write, in some higher programming language of your choice, C++, Julia, Python, whatever, gets broken down into assembler and broken further down, into logical circuits, which can be just expressed in terms of these NAND gates. So that's actually a pretty interesting thing. So this is universal. This is mimicking it one-to-one. So that means that this single neuron is computationally universal. So you can map every logical circuit built with NAND gates, or every other gate that you can represent by NAND gates, by an artificial neural network built solely from artificial neurons of this sort. Aha! So artificial neurons allow us to build neural networks that are computationally universal. They can calculate arbitrary functions that we want. So that's pretty cool. So neural networks are computationally universal. And it might be a coincidence of history that we are today building everything in logical circuits. That model of building logical circuits was just ahead historically than artificial neural networks. If for some reason the thing would have gone the other way around, probably would be thinking that way today and build our computers in a totally different way.
So is that an example weights that you've put to
What's that?
Mimic? Is that an example weights that you've put to mimic the NAND gate?
Yeah. So that's So of course you can this is an example of the weight that you can put. Of course you could have multiplied this by 2 and the weight
And you're claiming that mimics the NAND gate, or
yeah. So here you can just check. You put 0 and 0. Yeah. So that's 0. Yeah. So that generates exactly these kinds of outputs. So that's fine, but you could have chosen different numbers here as well. And that's actually that's the thing where it's exactly that's what's written down here. So the logical circuit is very fixed, while here you immediately realize that you can actually vary these weights just a little bit. And probably by just varying those gates a little bit, those weights, your neural network can acquire additional power and functionality in doing exactly that, varying the weights. So it seems that they're actually, a more flexible object than logical circuits to work with, but they have the same computational power. And they're universal. So that's what you want. You can do arbitrary things with them. So let's now take these very powerful elements, these artificial neurons, and build a network out of them. So one way of building a network that is often used is this way, where you do the following. You have a hierarchy of layers. So there's a first layer here, these gray neurons. That's the input layer. So that's where you have some input. So in this case, you have 5 binary variables that go in. They will be reduced to an output layer. In this case, these 2 neurons in the end, that will fire, and they will be 0 or 1, and then you have a binary output of 4, 2 to the power of 2. And between those are a couple of, computing layers, or as a computer scientist say, they're hidden layers because they're not the visible input or output layer. Okay? So that's a hidden layer, and there might be many ways, in that you can shape, these layers. How many neurons do you put per layer? How do you connect between the layers? So here you see something that is fully connected. So this neuron is connected to every one of the neurons in the next layer. Here the same thing, and they're in every step of the game that's the case. But that doesn't have to be that way. It could be, different. What you also see is that all the directions only work forward. So there is no neuron on this layer connected back to one in the previous layer. So you can traverse this network from the left to the right. That will be important. So it's a feed-forward network. So there's no returns. So that is a mechanism that you put in to make things simpler. It's certainly nothing that the biological system suggests that we should do, because that certainly is connected all kinds of ways, allowing for these loops. We will not allow for these loops here. So now there is a conceptual word that we will disillusionize right here. So computer scientists said if you consider hidden layers, and you could consider multiple hidden layers, then your network is deep as opposed to shallow. Shallow would be just a single layer between the input and the output. But if there's multiple layers there, 1, 2, 3, multiple, then you have a deep network, and what you perform is called deep learning. Aha. So deep learning is a very fashionable word that you hear in all kinds of contexts. Now we realize all it means is that there's a hierarchy of layers between the input and the output, and that is probably 3 or 4. So it doesn't sound to a physicist like extremely deep concept. That's all that there is to it. Okay. Good.
So that feed-forward way of doing things, is that just for simplicity?
So that's for simplicity, and we will see in just a step, why it makes things simpler. Of course, no one can tell you, what you have to do, in what you want to do. We will see, that the history of neural networks, they have tried, to explore all kinds of things, So they have, of course, been, networks with loops and all these kind of things, and you will hit different, difficulties. Probably I should put some numbers here. So the field of machine learning, and the way that I introduce it here is 70 years old. So the artificial neuron, the paper was written in the 1947-ish, so 1940s, in the Journal of Mathematical Biophysics. So there's several things to learn, So there's already a journal for mathematical biophysics in the 1940s, That concept was laid out already in those early days. Didn't pick up that much steam, Only in the 60s, was this concept made that, artificial neural networks are computationally universal. In the 60s, so 20 years later, that's when they realized, that they had a very powerful things. And now in the 80s, we will see what led to some wave of enthusiasm in the 80s, connected to this deep learning and feed-forward networks. And that comes when we ask about, how can we now generate a neural network? So now you're asking yourself, okay, I have decided on some architecture. This is my neural network. This is how I would like to design it. But now I have to choose a lot of parameters. Because every one of these links has a weight associated with it, and every artificial neuron in these hidden layers has a bias, a threshold value. So I have to assign these. But how do I assign these in such a way that I generate output in the way that I would like to have? Well, so what I will do is I will introduce in this first step a cost function. I will say, well, there's a couple of input variables x, and they they should create a certain output, a desired output, here, y of x. That's what I would like to have as an output, and the neural network will generate something else, some actual output, and I can just look at the distance between this input and the output, square it, and that gives me a cost function. So if that cost function becomes small, a minimum, then these two things are close, And for every larger values, they're further apart. So I want to certainly minimize this function. And I want to minimize this function by varying the weight and the biases, the threshold values of all the artificial neurons here in that network. So when I want to do this, I want to, the first step that I will come to me is that I will want to adjust something in the network. Oh, n is the number of neurons. No, it's the number of neurons, the total number of neurons. Yeah. So at the end of the day, it's actually not relevant here because it's just a normalization. Yeah. So n is the number of neurons.
Okay, so you expand your deep section that effectively brings down the cost. Is that
so
or is it the one stack that you're referring to?
So that's at the end of the day, n is a constant. Yeah. So in the net, the networks that we will look at here. Yeah. So we are in the process of playing with the network, we will only adjust the weight and the biases, and we will not make new connections, add additional neurons, change the layer geometry, this kind of thing. Yeah. So, but something that we will realize very quickly is, as I proceed to this neural network, this step function, it's a very nonlinear function. Yeah. So it makes everything nonlinear. Yeah. So if I change one of the weights, I might take one of these neurons and make it fire all of a sudden because now I managed to go above the threshold. So that will have the effect that a small change of one of the weights will have a dramatic effect on the neural network and its output. Yeah. So such a nonlinearity will make it particularly hard for me to adjust weights in the network. Yeah, because I would like to have ideally a situation where small changes to the parameters in the network will result in small changes on the output, and I can gradually follow now the direction of the ideal change where I reduce my cost function. So in order to do this, I will change the function, the calculation function on the neuron from the one where I take my input and I compare it to 0 and have the step function to a more smoother version. This is called a perceptron. This is called a sigmoid neuron.
Is this the output or the probability of the output?
So that is the output. There is no probability. Yeah. So that every neuron is a deterministic element. So there is no probabilities.
Why would we be interested in step function anyway? Why not some other function, something linear that also gives how much?
Yeah. So so the perceptron is just historically the first one. Yeah, because it reproduces this effect that you see in the biological system, that it fires only after a certain amount of input has been prepared. Yeah, and this step function models this in one way or the other. But of course, you can take this function and make it arbitrary changes basically to it. Yeah, but here the one concept that we now want to enforce is this one. Yeah, that it's a smooth function, because that will allow us to make these small changes result in small changes to the cost function. Yeah, that's the important step here. Yeah, and there's various other things that you can now try, of course. Yeah, and there's extensive things that people have tried in various contexts. But the important thing is it's not a probability. Yeah, it's a deterministic element in neuron. Yeah, so you calculate. So z here in this case again is just the scalar product of the weights and the input variables compared to that bias. Yeah, so x times w minus b. Cool. So now I have this effect, with these sigmoid neurons, that a small change in the weights will result in a small change of the cost function, and I can now track the cost function as I vary the weights.
Do you use a perceptron just for classification, or?
So the perceptron, was cool, because when we did this logical circuit, that made links easy, that we had this statement. But in the same sense that the perceptron is universal, the sigma neuron is of course as well. Yeah, because if I just stretch out my weights in a way that I'm in the far tails of this distribution, this function, then I will generate exactly the same types of outputs. Yeah, so I haven't lost anything in going to this smoothed out version of the perceptron. Yeah, so at the end of the day, you might say, well, you should never do this, right? Yeah, you should always do that.
Are you also changing the smoothness parameter for the sigma, because that's also a fixed thing forever?
No. So you can you know, the problem will be that there's a lot of things that you can vary now, yeah, and you have a very dedicated task that you want to do in the end, and you know, controlling that complexity, yeah, is a typical physicist approach to this problem. Yeah, we will be interested in that. Yeah, you know, computer scientists, you know, are more driven by application. You know, they will say, well, you know, my task is, you know, I want to have this car drive me to the store, and if that works, I'm just fine. Yeah, and I don't give a shit. Yeah, so about you know these things. So, but our you know approach typically will be different. Yeah, so before we make something work, we will start to explore these things. But we will see that we will get overwhelmed as well in you know the complexity of what's
I
there.
think my question is the only thing that you require is differentiability.
Oh yeah, yeah.
Or is something else?
No. At this point, all I want is differentiability. Yeah, so a smooth function. Okay, good. So now I have my smooth function, and you know now I can do you know this gradient descent. So I can you know this is very idealized. I can go and you know search for the minimum. Yeah. So this is just a quadratic function, and you know finding its minimum is very simple. It's actually not a very good picture for what's happening here because you know this function is it's a multi-parameter function. So you know the space that you explore will be a rugged landscape with lots of local minima, and there's a global minimum, and you're trying to find that. Yeah, and the complexity of that energy landscape or cost function landscape, yeah. Again, the typical physics question is, you know, how complex is it? You know, do you get stuck in local minima? Yeah, that is the stuff that we ask. You know, the computer scientists were much more concerned with something else. And that is, you know, how do you actually effectively implement this gradient descent? Yeah. So if you have these many different, you know, variables in this network here, you can of course say, well, you know, let's do something that we have learned in our computational physics class. You know, let's try a Monte Carlo type approach. Yeah, let's just, you know, go in here, like take this weight and change it a little bit, calculate the cost function, and then, you know, make a decision, Monte Carlo move, you know, whether we want to follow the minimum, you know, or not. Yeah, that is, you know, prohibitively expensive. Yeah, because you're making a little change here, and then, you know, calculating what the cost function actually does, you know, means you have to traverse the entire network. Yeah, so, you know, evaluating this cost function for every single move, yeah, you know, would you know dramatically slow down, you know, this entire process of adjusting these weights, you know, to find that minimum. Yeah, so that's when in the 1980s, yeah, this algorithm came along, you know, the back propagation algorithm, yeah, which now makes use of the fact that we have a feed-forward network and back propagates. Yeah, so what it will do is it will work, you know, the way back through the network and calculate all, yeah, the partial derivative of the cost function. Yeah, so the cost function with regard to the weights and the biases. Yeah, so so we are not super impressive as physicists. Yeah, of course you can do this. Yeah, you know, you just walk back and you know, okay, but you know, okay, so that's back propagation. Yeah, but once you have that, yeah, so you do this one sweep through the network, and you have all these derivatives. Well, then of course, you know, you can just look at all these derivatives and look which one is the biggest one. Yeah, so which one is the steepest descent at this moment? Yeah, and follow that one in your gradient descent. You know, make the next sweep from the back to the front. You know, again, decide which one of the many parameters that you have, you know, is the steepest descent, and then follow always, you know, that route. Yeah, if you do that, you know, you become faster. You might dramatically faster than you know the what I just described before. You change individual weights and you know then propagate through the network and calculate the cost function change. You know, make a Monte Carlo move or something like that. So this makes you faster, and this was, you know, what allowed, you know, for the first time in the 1980s to consider, you know, network architectures like these, you know, which were somewhat deep, yeah, which had a couple of layers, and which were trainable, yeah, so where you could effectively find the minimum of the cost function, yeah. So making, you know, this step, yeah, adjusting all these weights, you know, that's the computationally hard part, yeah. Finding, you know, what is good here, yeah, and that is only, you know, the weights and the biases for a given network architecture, yeah. So of course you could say, why, you know, why don't you make it a free parameter, the network architecture? Why don't you, you know, play with, you know, the smooth and all these things? Well, you could, but yeah, it makes it incredibly hard, yeah, to, you know, optimize all these things at the same time.
Can you comment on why back propagation is extremely efficient without actually forward propagation?
What's that? Why is it so effective? Yeah, so the reason is, you know, you might be like, oh, yeah, you know, always following the steepest descent, yeah. that shouldn't work, yeah, and that should run you into a local minimum quickly, and then you are stuck, yeah. So and then you might have a mediocre network, and then you're done. The reason why this works is that you're dealing with a high-dimensional parameter space, yeah. So so getting trapped at a local minimum is actually that easy, yeah. It's not that easy because there's always a way out because there's all these other parameters, all these other directions that you can follow, and that's why this gives reasonable.
I guess the question why backpropagation is very efficient to calculate the possible derivatives.
Oh, why? Oh, the point is the point is that all you have to do is you do one sweep from the back to the front, yeah. So and you basically take all these it's how's that rule called product chain rule, yeah, the chain rule, yeah. So it's a chain rule that makes you walk through this, yeah. In calculating this differentials, yeah, and then the key step is that afterwards, you select the biggest one, the steepest descent, yeah. Okay, that's it's a much more efficient way than trying to randomly find out which one it is, yeah. So what I proposed before is you go to an arbitrary step, you say, well, this one, yeah, let me try changing that in an arbitrary direction, the weight here, and let's see what that does, yeah, and that will not be good, yeah. We will come back to this step in a few minutes and see a little bit more what people have been developing in the last 30 years on top of this idea. Okay.
Do you say that the random one does not work?
The random one is just prohibitively expensive because it costs you too much for any random move to find out what the cost function is. Now if you compare that to classical Monte Carlo on the Ising model, you flip a spin, but you can quickly calculate what the energy change is. Because you can do this locally, yeah. You flip a spin. There's only so many neighbors, and the entire.
So is this C function calculation because it's like a couple of multiplications, isn't it?
Yeah. So that's an important point too. It's just a couple of multiplications. Yeah, you have to but still you have to process through. Yeah, making that cheap. These couple of multiplications. Yeah, will also come in later at a point. Yeah, yeah. Still, compared to just making one sweep, getting all the derivatives is much better. Good. So that's backpropagation, and that set loose another set of hype in the 1980s. Yeah. So many of my peers, they say, oh, neural networks, they were popular when I went to high school. That was because there was a time when people thought they had solved this problem of doing interesting stuff with artificial neural networks, when they had this backpropagation algorithm, and they could eventually train, optimize deep neural networks of this sort, and the language, deep neural network comes from that time. It's nothing new, yeah. So it's that has been used in their field for the last 30 years. Good, but somehow we know, that self-driving cars, chess playing computers, and these things haven't been developed in the 1980s. So something else, must have happened, since then. So let's try to move there and. I gave you now a very specific version, introduction of this field. Yeah, I introduced the artificial neural network and one way of setting these weights. But really, let's do this a little bit more systematic and discuss the three flavors of machine learning. Yeah. So here's flavor number one. That's the one that I alluded to just a minute ago. Yeah, that's called supervised learning. Yeah. So supervised learning means that I train, with labeled data. So training always means I set the weights and the biases in the neural network, yeah? And labeled data means something like this, yeah? So I have a data point, and I have an expected label. That's what I said before, yeah? We have an input, and we have some desired output, okay? So this might be a situation, yeah? So I have a data point, an expected label, and then I have a cost function, and the cost function works generally like this, yeah? So I have my expected label, and then I have the output of the neural network, which will be some function, yeah, of the input and these weights and biases, yeah, and I can change the weights and biases, but not the input, yeah, and then I have some function that I can calculate, from this pair, yeah, and that's how it works, yeah. So that's called supervised because I tell it, if you have this input, that is the output that I expect you to generate, yeah, yeah. So now train yourself in order to reproduce what I've just said, yeah. I label this data for you. The way that you do this is by stochastic gradient descent, that we have just heard. Yeah? So you try to minimize that cost function. So you go from one set of weights, W and B, to a new set of weights, W and B prime, yeah, by following, you know, the gradient of that cost function. So the gradient of the cost function, that's backpropagation, and then, there's a prefactor, that's called the learning rate. Yeah? So people will sometimes talk about this learning rate. Yeah? So it just says, you know, what you multiply, which constant factor you multiply to the gradient. Yeah? So how much you want to follow that steepest descent. Now you can adjust the learning rate over time, yeah, over time in your training process. Yeah, initially, you know, this, you know, learning rate, you know, this step width that you take following that steepest descent might be very large, and over time it might become shorter and shorter and shorter and shorter. Up, you will just invented another algorithm, yeah, and you will get actually a couple of thousand citations for just that idea. Yeah, so here we go. So so this thing will converge to the global minimum. It's similar to a Langevin dynamics in what, you know, physicists think about. Let's go to an example. Yeah. Yeah. So so the noisy part is that, you know, in the end of the day, the way that I described it, yeah, I went through and calculated every derivative. Yeah. At the end of the day, I might choose not to do that in every single step. Yeah, and that's where it becomes. Yeah. So otherwise, it's fully deterministic. Yeah. Okay. So here's a classic example. Yeah. So the Ising model, yeah, of machine learning is digit recognition. Yeah. So here's labeled data. Yeah. So here are digits. Yeah. Zip codes, and every digit, yeah, that is handwritten here has a label, you know, that will tell, you know, what the digit is supposed to represent. Yeah. So there is a standardized set for this, yeah, which is held at NIST, you know, the National Institute of Standards and Technologies, yeah, which has like 70,000 handwritten digits. Yeah, they're the standard set for digit recognition. They were written by federal employees in different states of, I don't know, and generated a little bit of variation. You can use, you know, 50,000 of these digits to train your neural network, and, you know, another 20,000 to apply it to, and then, you know, talk to your colleague over the phone, you know, how great you are in recognizing those digits. And that has been the game plan in machine learning for a long time. So these are 28 by 28 pixelated images. Yeah, so they will be the input to the neural network. Yeah, so 28 by 28 pixels. That means there is 784 input neurons. Yeah, that will, you know, encode the shading of, you know, this individual pixel in that image. Goes in here, goes into a hidden layer, a single hidden layer. Yeah, with, you know, say 100 neurons, and then there's an output layer with 10 neurons. You know, the digits 0 to 9, and, you know, they will fire. Yeah, and you know, will hopefully generate, you know, the right firing if it's a right digit. Yeah, so in this case, you know, digit number 9 should be firing. That would be the output. Okay, so that's digit recognition. Is an example of, you know, supervised learning. I give you examples. Yeah, then you adjust your neural network. Using exactly these algorithms. You can do this with 60 lines of code. Yeah? And if you do this, you get 95% accuracy. Actually, if you go to my website, I've done this last summer in my computational physics class to great success. Yeah? It's amazing for myself. It's amazing probably also for you that you can actually do this. Yeah? So you write, you know, 60 lines of code, yeah? And you do everything from scratch. Yeah? There's nothing, no library that you're using. Yeah? All you do is these matrix multiplications, yeah, so simple stuff, as you said, and you generate this 95% accuracy. So, you know, that means out of these digits here, which are only 10, you know, you probably get all of them right. That looks like a miracle to me. Yeah, it's very enlightening to do this. Of course, 95% accuracy is not very good. Yeah, it means that 1 in 20 is out of the book. It's wrong. That's not good if you're the postal service, yeah, and you have to do this for a living. You know, but if you do it for yourself, you know, only 1 in 20, that's pretty good.
So if you train it on these digits, now if I give an input of, if I turn the 9 upside down, will it still be able to understand?
Well, if you turn the 9 upside down, it's called a 6.
Okay, bad example.
So now if you flip this 3, yeah, that's tricky, yeah. So you will get, yeah, you will have a problem. Yeah, you see, there's people who write 9s that look a lot like 4s. Yeah, there's people that, you know, write 7s. To us Europeans, you know, this 7 looks a lot like a 1. Yeah, we have an extra bar in the 7 to make sure that we distinguish it from the 1. So there's all these ambiguous cases, yeah, and you will fail, yeah, and you will fail easily. Yeah. So as such, actually 95% is pretty good. If you look at some of the really shitty digits in this set. Still, you want to be much better, yeah, and you can be.
How fast is it? Would you say running on the Python with 60 lines of code? How fast is it?
Yeah. So how fast is it to program this, or how? No. No. This is actually very fast. So you can do this in class. You can train the network, yeah, within a minute, and then it will do it. Yeah. So yeah. So it's not slow at all.
Yeah, so like how many more lines of code to get to 99.99% or something?
Yeah, so it's not only more lines of code that will bring you there. Yeah, actually it's a new concept. We will come to the new concept in a bit. Yeah, yeah, and it will be you already see here you're doing something very rough. Yeah, so you take a 28 by 28 matrix, and you make 784 individual entries out of that. Whew, yeah, so you forget about everything. Yeah. Which pixel is neighbor to which one in this, yeah? You're just throwing that out of the window, yeah? So you think, that the neural network will just take care of that, yeah, in its hidden layer. Well, yeah. So it's actually one of those things, where it's clearly not scalable, yeah? Today you take your photograph, yeah, it's 5 million pixels. Yeah, so if you take 5 million pixels as individual inputs, you throw it in and now say, where's my cat in the picture? Yeah, oh no, yeah, it's not gonna work. Yeah? So here's a physics example, yeah? So we just said, I can, distinguish 2 different digits. Let's distinguish 2 different configurations of Ising models. So here's an Ising model in its high temperature, paramagnetic phase. Here's an Ising gauge theory in its ground state, which enforces that on every single plug. Oh, so it means that the Ising degrees of freedom are sitting on the bounds of a square lattice, and you enforce that there's an even number of spins pointing up or down per plaquette. So now you look at this, and this is a high temperature state of that model. That's a low temperature state of that model. And what's the difference? Yeah. So what we will learn in the afternoon is that we can do this. Yeah. So we can distinguish these phases with 100% accuracy. Yeah. So no fooling around. Yeah. You try to do this, it's hard. Yeah. So here we see that this will help us. Okay. So we can somehow distinguish physics phases with the same type of codes that do digit recognition if we train it in a supervised setting. Yeah. So if we generate I don't know 1,000 instances of the high temperature phase of the Ising model and 1,000 instances of the slow temperature phase of the Ising gauge theory, yeah, it will eventually be able to distinguish the 2, yeah, and say this is the one, this is the other.
What if you change to sigma X spaces? What?
Yeah, so you mean, let's make it quantum? Yeah. Good question for the afternoon, we'll come to that, okay? Okay, so...
100% accuracy is a little... are we talking about...
Man, these guys wanted to have the paper Nature Physics, okay? Yeah, so, no, so that's, of course, at the end of the day, there's always, a problem somewhere, yeah, and it's not going to be a solid 100%, okay? Okay, so we had said, there are 3 types of learning. So the first one was supervised learning. So the second one is unsupervised learning. Okay, again, we start with data, but this time there's no labels. I'm not telling you what I expect as an output. So instead I just generate, for you, n input variables, and I say, well, that's it. But probably, they follow, some distribution p of x. I would like to know what that function is, that distribution p of x. Yeah, so that's my job now. I want that the neural networks learns to model that distribution. So that it can also churn out a couple of numbers, yeah, that follow the same distribution as the one that I fed in. Aha. Yeah, so that's unsupervised learning. Try to identify a distribution. How do I do this? Again, I have to introduce some cost function. And what is typically used, in that field is called the Kullback-Leibler divergence. It's a measure that calculates for 2 distributions how close they are. Yeah. So let's just put it that way. Yeah. Yeah. So this is this. You have 2 distributions. The unknown distribution p of x. That you try to find out. Yeah. And f of x is the distribution generated by your neural network. Yeah. And there's some measure that tells you, how far these two distributions are apart. Calculating it is not that easy, because it needs knowledge about both distributions, and that is not readily available. But the nice thing is that calculating the gradient of that cost function is something that you can do more easily, and that's why you can do this. Okay, let's not go further into detail here. I can talk about this in the coffee break or other places. Okay, so unlabeled data, try to find a distribution. Here is an example of that. So let's again, start with a common world example. So let's do this. Let's have a couple of people in the room write a sentence. So Cornell is the best place for a summer school. And then after 3 people have done this, a lot of times, if you're a bad student, probably Una makes you do this, a few hundred times. Let's put this into a computer, and the computer has to realize Una has 3 students. 1, 2, 3. They have 3 different types of handwritings. That's what the unsupervised approach is here. So we realize different types of handwriting. So student A has this writing, student B that one, and student 3 this one. And then after you have learned this, you can start writing arbitrary stuff. You have learned the handwriting of the first student, and you can write a sentence. You have learned the handwriting of the second student, you can write some other sentence and so on. So that's forging handwriting. So you learn that there's different ways of writing. Here's a physics example. So let's do Monte Carlo. Oh, here's a question.
For the handwriting example, do you ever tell it how many different people there are that are writing?
No. So that's part of the trick. So that you get all this data, and you realize there's actually 3 sets that are close by. So and that's exactly very much wanted in your big data analysis. You're trying to find out how many different types of shoppers are there on Amazon. Oh, only 3. Morning buyers, evening buyers, I don't know. Stuff like that, and morning buyers buy different stuff than evening buyers. Okay, so in a physics context, here's what you might want to do. Oh, here's another question.
In the previous example, what is x, what is p of x?
So x, the input, the data is this writing. So the first student writing. He writes arbitrary stuff. You make him write down lots of poetry from Goethe or whatever. And you see that there's only 26 different letters. And they come in a variety of shapes, and this is the distribution that you learn. You learn a distribution for the C's, for the O's, for the R. Then you distinguish it from student B, who does apparently the same stuff, but has a different distribution of how these letters look like. And then at the end of the day, you just type something. Actually, you type something into that web interface. Some sentence, and then choops, comes out in the learned distribution. So now it will just take one of the m's, sampled from the distribution it learned from the m's, 1a, and so on.
What will happen if we just remove one distribution function? So for example, we have, for unsupervised learning, only 2 sentences, and here we have 3. And we know that the set differs only for 1 sentence. Will it still work?
No. So when you're asking, no. So that this is 3 and this is 3 is just my example. This could have been 25 different types of handwritings.
No, of course. I mean, if we have, for example, 25 different types of handwritings and then 27 arbitrary sentences.
Oh no. So the way that this is down here is that I said, take one of the handwritings, like the first one, and now write what I want you to write. So the second step is that I'm after the learning. So now I know what I have. I have 25 different types of handwriting. I choose one and say, now you write in that handwriting the following sentence. And it generates from its learned distribution a sentence that hasn't been put in the beginning. So you start writing arbitrary stuff. So students writing the excuse in their parents' language and kind of stuff. So
So this is essentially sorting as far as at this level?
So there's multiple steps, going on, So one is, learning that there's different distributions, and one is, what that distribution is. So so there's handwriting A, handwriting B, and handwriting A, has There's a small variance when it comes to writing a little a. You know, guy number B, you know, always writes different. Yeah, so it's a much wider distribution. Yeah. Well, let's go to the physics example to make this clearer. Yeah. So here's you know, something that Lai Wang and Liang Fu's groups have independently, you know, came up with this year. It's actually very nice. Let's do Monte Carlo. Yeah. So we want to sample, you know, configurations in our numerical technique from some distribution, like Boltzmann distribution. Okay. Good. But let's say we don't know as a machine now about the Boltzmann distribution. We only see, you know, what gets accepted and what gets rejected, yeah, in Monte Carlo moves. So we would like to learn that distribution. Yeah, so my neural network is supposed, you know, to learn that distribution. Yeah, so it's supposed to mimic, yeah, that Boltzmann distribution and now generate on its own, you know, suggestions from that distribution. And the nice step is, if I do that, you know, I can, you know, generate very high acceptance rate in my Monte Carlo moves. So if I know, you know, how the Boltzmann distribution looks like, I can create, after having learned the distribution, you know, moves that will always get accepted because the acceptance probability at the end of the day will look like this. You know? So it's always, you know, if you go from one configuration to another configuration, it's the quotient of the probability of the new step versus the old one. And that gets multiplied now by the inverse, you know, of this distribution that you generated them from. So if the two distributions are exactly the same, this becomes just one. Yeah, so this is extremely helpful. So you can find out, you know, what a good move is. Yeah, and you can perfect that. Yeah, so you suggest something and it will get always accepted. So your autocorrelation time will dramatically reduce from, I don't know, it takes you, you know, 1,000 steps to come up with the right move to immediately you have a good idea. And that's exactly, you know, what they're employing in, you know, trying to track problems that are extremely hard to calculate, you know, where the distribution is, you know, calculating the update, you know, this acceptance rate is so expensive that you can only make a few moves. Yeah? So, for instance, fermionic Monte Carlo will come up in the afternoon as well. Is of that sort, very expensive type of calculations. You know, suggesting just the right thing, if you have learned it somehow, will be an incredible step. Good. So we said there are 3 types of machine learning: supervised learning, unsupervised learning, and the final step is reinforcement learning. Yeah, so you reinforce something. So you generate data and you get some feedback and you see, aha, this is the feedback, let me come up with some strategy to generate the right kind of data. Yeah? So what you will generate is a scoring function, yeah, that will be applied to the output of the neural network. Yeah? And what you are supposed to find out is, you know, what is the best, yeah, neural network, yeah, that will minimize, you know, the scoring function and thereby generate a strategy. Ooh, so this sounds very complicated. Yeah? So here's how that learning works. Yeah? So you produce data, you get feedback, you know, from that scoring function. You know, it's called the reinforcement stimulus. You did a good job. Ah, you didn't do a good job. Yeah? You always try to do a good job. Yeah? So you adapt your network and you try to be better. Yeah? And then you produce new data. You find out whether you now get positive feedback and so on. Yeah? So that sounds very abstract. Let's do this by example. So the example is exactly game playing. All the game playing is by reinforcement learning. So AlphaGo, yeah, so the Go player, that was, you know, reinforcement learning. So Giuseppe gave me these very nice videos. So if you were born in the 80s, you played Atari, card games. Of course you weren't, yeah, but I did, yeah. And you played this extremely simple game of Pong, yeah, where you try to, you know, get bricks out of the wall up here. And you see after a short training period, yeah, the network, you know, which, you know, follows, you know, this is a scoring function, you know, your score, yeah, was always very low and it did a shitty job, okay? Yeah, it didn't realize, you know, what it's supposed to do is, you know, move the bar, yeah, such that the ball gets reflected, yeah? So that didn't happen here, yeah? But you keep telling it, you know, the score for every move it does, yeah? So the one here on the left, and after you have done this a couple of hours, man, you get a pro, huh? Okay? And it's actually really good. And I, as a kid, went through the same thing. You know, I learned my trick, and you learn, you know, the following trick. Ha! Yeah? You have to get the ball around it, okay? And this is what the neural network will also do, yeah? So after a little bit of trading, it will realize, you know, what's supposed to do is, you know, get the bar at the right position so that it doesn't fall out. And eventually it will find out that it really what it has to do is you get it behind it, yeah? And then, you know, your scoring function is big as well as small. So that's reinforcement learning. So, so these are the three types of machine learning. The physics example for reinforcement learning will come in the afternoon. So now my time is actually up. So I could either stop here or go for a couple of more minutes. You know. You will see it's your own work which is coming up. So, so let's understand. So let's the pre-processing. Let's understand why we can do digit recognition so much better. Okay. So here's a couple of digits, yeah, and you see the variation in people writing ones, threes, zeros, yeah. So how can you improve on this? Yeah, it's called convolutional neural networks. What they will do is they will look for recurring patterns, or so-called filters. Yeah, so you will see that like a 1 is just made out of very basic elements. Yeah, and a 2, has some other elements. Yeah, and now what you will do is you will take data from the image and take a filter. This is the filter which has this shape, and then you will convolute the two, which is a matrix multiplication, a piecewise matrix multiplication. So you take the first element here, multiply it with the first element here, the first element here with the first element, and so on. Yeah, it gives you numbers, yeah, and then you sum all of them up, gives you some new number, 5, and that's your new output. And now I can do this, and I can take that filter and slide it over my input variable. Yeah, in doing so, I will get hits, where this filter works very well. Yeah, and as I move through, I will encode, how well the filter works, yeah, on, a set of 3 digits in this number, and the convoluted image will look like this. Now you say, well, this is a 2, I don't know what that is, yeah, so why does this help? Yeah, it helps because it will, generate information that is now actually taking, 3 by 3 matrices and encoding the information, in those 3 by 3, so local information, and it works it up into something new that you can then feed into the neural network. So that's why we call it pre-processing. This stuff you will now feed into the neural network and say, well, now recognize what that is. And as I said, the digit recognition that we did before was so stupid to just put all these 700 something digits, pixels into the neural network without any locality information. And that already gave you 95% accuracy. Yeah. So now I generate this locality information by sliding this filter over the network. And as a bonus, I will make the filter a variable as well. So I'm not telling what the filter is supposed to be. It's a 3 by 3 matrix that will also optimize. That's going to be a crucial step. Yeah, it is this step, the convolution, yeah, before feeding the convoluted image into the neural network that has led to this revolution in 2012. So it's really there's a stepwise function in image recognition. Before 2012 was pretty much mediocre. Afterwards, it was fantastic. Okay, so you can take these images, run them through a neural network, and say, well, this is a container ship, this is a leopard, this is probably a dog. What you cannot see is, he's hiding behind some cherries. Yeah, so these are really obscure images. Still, the computer manages as well as you do in seeing these things that you're seeing there. 2012 is the year where this happened. Yeah, convolution plus neural networks. Ever since, we are flooded with, working image recognition. So the fact that Microsoft can build this computer, a piece of hardware that recognizes your face, only possible because of this, but it works to the extent that they actually put it as a feature and sell it to you. Yeah, so you should think they're very conservative. Yeah, so they will only do this. Physics example, worked out here by Frank and Yuna, very nice. Different type of pre-processing of the data. Okay, so now we have some physics-y thing, yeah, so probably we have some quantum many-body system, and it has, the most obscure thing that we know about that is, topological order, and we want to see that. Yeah, and what they have suggested is, let's do quantum loop topography. Here's how it works, yeah. You have some lattice model, and you have a pre-processing step that will look, over, the wave function of, your system, and it will look, at little loops of, varying lengths. This is our filter, yeah, and we'll calculate something like this, yeah, 2-point operators that form loop. It's a way of generating additional information out of what is already there, putting this locality in there, yeah, and then that image you throw into the conventional neural network. Okay, and if you do that, you can generate curves like these. So here's some toy model. which as a function of some parameter, kappa, yeah, which is, the hopping between, sides on a given lattice, will, drive your system from a trivial band insulator into a churn insulator. A churn insulator is a topological insulator, yeah, so it has a topological churn number, yeah, and the transition happens here. And by doing this preprocessing, with, loops like that, yeah, and then, generating images and feeding them into the network, you can generate a step function like this, where you go from 0 to 1, yeah, exactly at the transition between these two phases, so it can identify, correctly that the phase on the right is very distinct from the phase to the left, yeah. So that's pretty amazing, yeah. So that sets the tone for what you want to do in the afternoon. We want to play with these quantum many-body systems, and we want to look at those and find out, whether can we do this, yeah, identify phase transitions, and we will, put many things at play, like these pre-processing steps or other things. Here's a question.
How do you get these configurations? So you did some.
Yeah. So that's you can do various things. Yeah. In the afternoon we will hear a lot about Monte Carlo. Actually, what did you do, Frank, to get this? Yeah, same thing. Yeah. So you need some way of generating pictures and what the right pictures are. There's typically another numerical technique, applied, generating those images, and then, you apply them to this, okay? Okay, so I'm 5 minutes over my time, so it's need for speed. Last slide, and it comes to the question that was raised here. Someone said, this is all simple stuff, it's all matrix multiplications. Yep, that's right, yeah. That's why, there is a lot of open source libraries like the one from Google called TensorFlow that will allow you to play Lego with neural networks, take different convolutional layers, neural networks, play with them and put them onto, NVIDIA's latest hardware, graphic processors. Graphics processors were made, yeah, for matrix multiplications because that's, what it is, to make an image, rendering. Yeah. Now they realize they have the best market ever, so they can actually perform these computations that are needed, in the training of the neural network super blazingly fast as compared to CPUs. Yeah? So this is the right time to invest in NVIDIA, whose stock has tripled, 3 times only in the last year because of this. Their stock has never done anything. Yeah? But now all of a sudden, yeah, they can sell, for instance, to me, a graphics card that you can put into a computer for $1,000. They sold it to me for $12,000 because I want to put it into a high-performance computer. Yeah, and it really is very, very nice. Yeah, so GPUs are having a heyday right now in doing matrix multiplications for neural networks. Okay, so with that we stop, we take a break, and we reconvene in the afternoon.